Thanks, Arasu, for that welcome, and thanks to the faculty of the university as well for giving me this opportunity to present this today. It's quite an unusual audience for me, to be honest, and you've seen my title on the screen. What I hope to do is demonstrate how throughout my career I've tried to enable opportunities for athletes ultimately to enhance their performance through applications of primarily biomechanics, but also a few different technological interventions as well. A few biomechanists in the audience. I hope you're not too disappointed that I'm not going to get too much into the detail. I'll try and highlight a bit of that, but hopefully it'll be a fairly high-level journey through some different applications that I've had the pleasure of being involved with. A few of you might recognise the younger me, but essentially kind of why sports science, why am I here? Probably like lots of sports scientists, I'm a failed athlete. I wanted to play sport for a living, didn't succeed at that, and decided that perhaps the next best thing was to try and work in sport. So I went and did sports science in Bath for my undergraduate. Was lucky enough to spend 6 months out at UNLV in the States, where I got the biomechanics bug, essentially. And as someone who, I wouldn't say liked maths, but maybe had an aptitude for maths and loved sport, realised that biomechanics was where I pretty much could see myself going as a career. Getting back to Bath then for my final year, I was fortunate enough to do an applied research project with some rugby kickers, actually at Cardiff Blues Academy. And this paper was one of the first ones I published, and probably a big career highlight for me was the fact it actually got featured on the front page of the newspapers during the Rugby World Cup in 2007. So I'd kind of had that taste of doing applied research, working with athletes, and actually seeing kind of the public exposure and interest in this type of research as well. So that was, again, another kind of confirmation for me that this was somewhere that I probably wanted to go and take my career, even if that maybe was a career highlight and we've not made the front page since, unfortunately. There's a few people I just want to recognise as well, important ones at this stage before I kind of get into the details of my talk. So when I was at UNLV, I was very fortunate to have a mentor in Professor John Mercer, who pretty much took me under his wing. He took me in his house with his family for the first few months, gave me free rein in the biomechanics lab, got me involved in a few different research projects where I kind of, I guess, learnt my trade and learned from the postgrads in the lab at that time, and that really gave me my kind of keen interest in biomechanics. I then went back to Bath to do my PhD. My two PhD supervisors, Grant Chawatha in the middle there, and Aki Salo, who's caught me completely by surprise turning up today. I spoke with you, I think it was last Monday, wasn't it, to run a few last ideas ahead of this, and you kept completely silent, and now you've appeared in the foyer this afternoon. So thanks for coming all the way from Finland to see this. I really appreciate it. They both gave me, I guess, a really solid grounding in the biomechanical methods and developing me as an independent researcher capable of challenging and questioning assumptions in biomechanics, and I'll touch on that in a minute, but also ensuring that everything we did was very applied and always kind of addressed real-world questions in sport. I've been fortunate enough to work with some great coaches as well. One in particular, any of you who know your rugby from back in the late 90s might recognise John Callard there on the left. He was a coach at the RFU when I started working in Twickenham in my first role at St Mary's. And I'll touch a bit more on the work I did with him later on, but he's always been a fantastic kind of mentor for me of helping me apply my work in the real world. Finally, Liam, going to get a mention as well. So since I've moved to Swansea, Liam's been my line manager officially, but also a great kind of supporter and mentor, and someone who's always kind of given me lots of opportunity and given me, I guess, the chance to run with projects, to take them over, and again, really thankful for all those opportunities I've had since I've moved to Swansea. And finally, probably a wider kind of network of people, and I'll touch on this a bit more in a second, is, as Arasu mentioned, ISBS, the International Society of Biomechanics in Sports. So I've been a member of them since I was in the last year of my undergraduate in 2005. And it's been a really valuable network for me. And actually it's helped me develop collaborations with people all around the globe. So a lot of these collaborators I've kind of worked with over the last sort of 17, 18 years have come from links created through that society. And I'm now at a point where I'm, as Arasu said, much more involved in the leadership of the society myself, and really enjoying trying to kind of strengthen these links and keep building these collaborative networks. Okay. This is what I want to hopefully try and get across today, and I'm always nagging my students about a nice clear aim when they start their presentations. I'm not convinced I've managed that myself today, but hopefully this is what you'll be learning a bit about as we go through. So I'm going to give some examples of how I've used biomechanical theory and methods to understand movement, because ultimately for me as a biomechanist, I see my role as looking at athletes' techniques, understanding those techniques, and then trying to identify ways in which changes in those techniques might be able to enhance their performance. And most of what I'm going to talk today is about performance enhancement and change that should affect performance. So obviously injuries will be considerations as well. I'll touch on that once or twice, but primarily we're talking about trying to enhance the performance of elite athletes. And I'm going to split today's talk into three main applications that I've had kind of the pleasure of working in over my career. So firstly, focusing on some sprint acceleration work. Secondly, moving on to some rugby kicking research. And then more recently, looking at some heated garments which we've helped to develop for athletes as well. So slightly less biomechanical, more on the technological side of things. But I'm going to just talk through each of these three different applications today. And hopefully what I'll demonstrate as well, as I perhaps alluded to in terms of my PhD training, is how there's kind of this overriding thread of the importance of the data analysis and the methods behind all of this. So although the research itself is very applied and very focused on trying to intervene and affect elite sport, it's been crucial that we've had some really solid kind of underpinning science behind all of this. And then most importantly as well, a bit of a look to the future, or the current and the future, and where hopefully we'll keep taking this in years to come. Okay. Just before I started my PhD was the Athens Olympics 2004. And this was the finish of the men's 100 metres. So there was only 0.04 of a second between the athlete that won the gold medal and the athlete that finished fourth. So a perfect illustration at that time of the importance of actually a really small effect on performance and what it could have on the outcome of something like an Olympic final. And my PhD was embedded within a group of British athletes training in Bath at the time. And the coach there was very focused on trying to improve the starts of a couple of his sprinters. Sprinters will spend typically around half a second from when the gun fires until they leave the blocks, and they'll leave the blocks at about a third of their top speed. So it's a really crucial phase where you can shave a few milliseconds, a tenth of a second off fairly readily with some good interventions to affect technique. So that was our challenge, to try and do that. Now, sprint acceleration wasn't a new field, it wasn't a new kind of topic at that time. Researchers had been looking at it since 1934 was the first study I think I found, where people had measured forces during the sprint start. But one of the biggest challenges when we started to try and understand this and look at how we might be able to apply this research to working with this group of athletes was actually how conflicting a lot of it was. And one of the biggest things that became an early focus in this work was identifying what assumptions had been made in the design of a lot of this research and what influence that had then on the conclusions that were being drawn by these researchers. And one early example of this was actually kind of the first paper I produced in my PhD, which was understanding how the way people measured performance, so essentially the biomechanical variable they used, how that had a key influence on what was identified as a good technique and a less good technique. And if people had used different measures to quantify whether someone was a good starter or not, they would get completely different pictures of whether those techniques were good or not. And that actually explained quite a lot of the kind of conflict in the literature that we were seeing. And at that point, we developed and proposed a new metric to actually assess performance. So suggested that measuring the power they produce in the blocks, rather than other kind of velocity or time or acceleration-based measures, would give us a much more objective picture of performance. And that's now one that we've kind of validated, demonstrated can be measured quite simply with videos out in the field, and it's used fairly widely in research and in practice now. A couple of other key assumptions that we came across and we challenged. There we go. Is the role of the foot. And I'll touch on this briefly now, but I'll come back to it. If you just watch this foot, hopefully the video will play again. Up until this point, the foot had typically been considered as just a rigid lump. in most research. But if you watch it during the late part of the stance here, there's quite a lot of motion around the metatarsal phalangeal joint, the balls of the foot. And we actually showed that ignoring that could underestimate some of the work done at other joints or overestimate some of the joints by up to 30%. So really crucial to actually include that motion in our models of sprint technique. And again, one final one, perhaps a bit more of the detail for the biomechanists in the audience, but we're all really excited by joint moments. So essentially the effects of forces about joints that cause our movement and that are really kind of fundamentals to us as biomechanists. Now up to this point, again, there'd been joint moments kind of looking like these squiggly lines on the bottom here, with lots of big ups and downs in early part of stance. No one had really offered a physiological explanation for these. It was very hard to actually do that. There was no obvious reason why we'd see such big changes in moment in what was really just 10 or 20 milliseconds. And actually what we demonstrated when we got into the processing behind it was that they weren't real. And they were an artifact of poor data processing that had just been kind of passed down the chain and done by default by researchers just picking up the same techniques. And actually we demonstrated it was a much more kind of gradual and consistent change in these moments in that early part of stance, and that was something that kind of had been overlooked in the previous literature. So lots of kind of assumptions had been challenged. That ultimately then gave us the opportunity to actually start trying to understand technique without falling into the same traps as some of these previous researchers, essentially. And where I've spent a lot of time, and a lot of my students have spent time since, is trying to understand the effects of how someone lands on the track when they kind of hit the track, the body configuration, the body position that they're in. And one particularly important variable is something we call touchdown distance. So essentially, where is their foot, kind of that blue dot you can see on the screen there, in relation to their centre of mass. And if it's quite close to being underneath it, when the sprinter then extends their leg and kind of pushes against the track, they'll largely push themselves upwards. Okay? If we can theoretically get our sprinters to land with that foot further back behind their body, then when they get that leg extension, they'll have a greater horizontal component to that force. Okay, we'd call it a better ratio of forces, and ultimately then more horizontal acceleration, which is what we want to see in the start. So we spent quite a lot of time looking at technical changes and how we might be able to influence this touchdown distance and what the effects might therefore be on performance. One of the challenges of trying to do this, particularly when this was still working with our kind of elite group based in Bath during my PhD, was that we can't just go out to sprinters and say, let's try this, let's change this, let's see what happens today. Because they've all got very kind of controlled programs. We can't go out and do experimental research studies with them. But that's where computer simulation modelling comes in. And a big kind of challenge we had to overcome at this stage was actually trying to develop a simulation model of a sprinter that we could ask these types of questions with, essentially. So it looks a little bit dated now in terms of some of the simulation models you might see nowadays. But this was one of the first ones that actually looked at simulating a sprinter and trying to understand the techniques of sprinters through computer simulation. And this was where, I mentioned earlier about that joint in the foot, I was banging my head against the desk for months trying to get this sprinter sprinting and not belly flopping or somersaulting or doing all sorts of other things. And then as soon as we made that change into the foot having that joint and changing the way the forces were produced underneath the foot, we suddenly got something that looked a bit more like sprinting. And it developed a model which enabled us then to ask all those what-if questions that we couldn't do out on the track with sprinters. So I'll take you back to that touchdown distance question. So now we could have the fun with the model. This was the easy bit. Let's change things about the way our computer person is moving, and let's see whether we could improve their performance. So on the left-hand side here, this would theoretically be our foot further back, hopefully a better ratio of forces, a force vector that's going to push them more forwards and not so upwards. And the sprinter that we were working with, he landed with his foot about 8 centimetres behind his centre of mass. And all the coaching theory, all the kind of descriptive and empirical evidence would suggest if we were to model his performance, if his foot was further forward, it would be worse. If his foot was further back, he'd see an improvement in performance. And we asked that question then to our model. And we saw what we thought until we started to take the foot further and further back. And it didn't do what kind of theory had suggested. Okay, and as we dug into the model, and that was the beauty of then having this, so we could look at why that was by looking at all the different features within the model. Okay, we saw that we were correct in that, yes, that force vector was more horizontally orientated as we took the foot further back. But unfortunately, it was also smaller. They weren't able to physically produce as much force from that configuration. And actually that led, for various other reasons as well, to a lower performance outcome. So something that kind of challenged the existing coaching theory at the time, and we were able then to use this model with the data from our sprinter and actually demonstrate other ways in which their technique might be able to be enhanced. One of which would be through a stiffening of the ankle joint rather than worrying about changing where their foot lands at touchdown. Okay, so this was me going into my PhD, kind of thinking about the small changes we might be able to make in performance and what implication they might have on performance outcome. I never got the chance, unfortunately, to then apply those model results to the sprinter or the main sprinter we were working with due to form, injuries, time, lots of other kind of factors that kind of had an influence on it. Even if we had, just as I finished my PhD, this was the next Olympic Games. And actually, probably even the 1/10 of a second we might have helped shave off wouldn't have made much of a difference. And that was a reality check for me probably at that stage in my career where I'd been so immersed in this one kind of very focused topic, and again it's probably a nod to particular PhD students in the room, about the importance of seeing the bigger picture of this as well. And hopefully a lot of the stuff I'll go on and talk about in some of the other applications today will demonstrate how a more interdisciplinary approach has been kind of used in some of these different questions as well, to make sure we're looking at the bigger picture rather than really focusing in on what has been really valuable kind of fine details of technique, but actually at times kind of missing some of the bigger picture elements that also need to be considered as well. So we've done a lot of research understanding technique, identifying ways in which technique could be improved. In the last few years, I've had the good fortune to actually be working with some great students who've now been out and made a difference with this, James being one of them. And he's been a coach with Harlequins Rugby. And I'll try and just briefly explain this data that's on the screen. So this is just one of his athletes, one of his rugby players. And what James tries to do with them is make them better accelerators, make them faster, based on essentially that kind of body of knowledge we've all developed over the years around different techniques. But he treats them all as individuals and understands how each person sprints differently. So all the pink blobs on here are what the sprinter used to do before James started working with them. It's their technique just kind of plotted on a space, essentially. And what James wanted to try and do was shift their technique in a certain direction, which was down and to the right. And he successfully did that over about 18 weeks worth of technical training with them. Most importantly, those blue blobs get a bit bigger, because that's essentially their performance level. So he created the kind of desired change in their technique, shifted them in the way he wanted them on this map, essentially, and also made them better accelerators. And this kind of individual specific intervention has been something that's kind of, again, James has really championed, but something where it's been really nice to see a lot of the underpinning theory we've developed now being applied at kind of the highest level elite rugby players. And just one second one again, which more recently with colleague Sean, who I think is in here in computer science, where we've developed much more technological intervention. This was with novice sprinters. So trying to develop a biofeedback tool, essentially, where they could learn how to do a good sprint start. So we hooked up with our Vicon system in the lab, some smart lights, and ultimately we could track the body positions of those sprinters. And when they were in a good set position, based on our research, that start line would turn green, and they'd be able to learn to adopt that position through the feedback that they were getting from the system. So a lot still to do in kind of both of these applications. I'm going to move on now to kind of the second part of my talk, where we'll focus on a completely different application, but rugby kicking. Okay, I'll let you just watch this clip. This was the 2011 World Cup final, about 65 minutes in, I think, and Trinh-Duc missed a kick with France 8-7 down to the All Blacks. No more points were scored. Okay, lots could have changed, but if he'd made that kick, France would have been 10-8 up. The All Blacks might not have won a home World Cup. Things could have been very different. Okay, and there's a lot of research which suggests goal kicking is a really, really important part that affects the outcome of these closely matched games, particularly in knockout rugby. I mentioned earlier that I had the pleasure of meeting John Callard around this time in 2011 in Twickenham, when he was working as a kicking coach with the Rugby Football Union. And we essentially, probably at the time was quite ambitious, but tried to embark on a programme of looking at the techniques of all of the players coming through the under-20s system and trying to build a profile of these kickers, ultimately to answer John's question of how we can develop players who can kick long and straight. And for the Welsh of you in the audience, obviously an adopted Englishman, but this is still one of the most impressive kicks I think you'll see. I'll just put it back on again. So Paul Thorburn in the 80s, and this is where we wanted to try and get kickers to. So capable of kicking these long distances, but capable of keeping it straight when doing so. And I'll touch on kind of some of the technical features which we've revealed that underpin that in the next few slides. This one was a little bit different from the sprinting research. So when we started to embark on this, we didn't have that kind of big body of research from 80 years or so that actually gave us a pretty good picture of how the movement was performed and what the techniques were. So it was a slightly different approach this time, and Alex is on the slide there. This was a large part of her PhD, was actually doing some fairly fundamental research to understand the mechanics of kicking. And I was fortunate enough as well to spend a few different weeks in Japan working with a couple of groups out there where we were, again, using some of their techniques and different, essentially mathematical and data analysis processes to really get into the nuts and bolts of how kickers are able to achieve high and accurate foot speeds. And I'm just going to touch on one of the key findings from this that hopefully you'll be able to visualise as we go through the screen here. And this is one of kind of Alex's really key papers that came out and really demonstrated some key features that explain why some kickers are better than others. And I think this view you've got on the screen here, if any of you watch much rugby, you'll have seen these spider cams that are above the pitch. That's kind of how we're looking down at players when I show you some data in a second. So one thing that we identified, and we split our kind of big group of all of these kickers that we studied in the lab over this kind of 5-year period into 3 groups essentially. Those that we could crudely classify as short kickers, they couldn't obtain the long distances. And then the other 2 could kick it over long distances. Some of them were very capable of keeping it accurate, others less so. Okay. And what we're seeing here is the angle of the pelvis, sort of crudely drawn with that red line on our kicker there. The short kickers simply didn't open their pelvis out enough. They didn't get that kind of stretch in the pelvis. They weren't generating, therefore, the kind of ball velocities of those other 2 groups. Okay, but our long and straight and long and wide kickers, very similar in what they were doing in that part of their body. As we move further up the torso though and look at what their upper body was doing, that was where we saw some quite fundamental differences between these 2 groups. And actually these upper body movements, and this all started to link back to that early work we'd done with the arms, where we understood what the arm of the kicker was doing, was quite a big explaining factor in why some kickers were able to achieve high performance and others weren't. And this has now become a big part of John's coaching practice, and a lot of these measures that we kind of identified here in Alex's work are now a fundamental part of his kind of field-based coaching and feedback interventions he does with kickers, looking at those upper body motions in much more detail. And it seems to be a thing again with Rugby World Cups. This was the 2015 World Cup when we were right in the midst of all of this work. And again, really nice to see sort of the public interest in this type of work. And this actually led to a few questions around injury risks as well. So although I said a lot of my work primarily focuses on performance, we can't always just consider that in isolation. we've always got those other questions as well. And we were fortunate enough at the time to do a bit of work with Scarlett's as part of Steph's postgraduate work, where we didn't just look at goal kicking, we looked at a range of different types of kicks. We took our Vicon system out for a day out from the lab, and then we were able to start kind of modelling some of the muscle tendon unit mechanics as well as just what we'd call the kind of skeletal mechanics of the system. And we were also fortunate enough to combine this with data from a season's worth of matches and injuries over 16 seasons in the Premiership as well, and build this kind of profile of who sustains injuries during kicking across a team. Okay, and I'll just try and explain this one because it's something we're really trying to understand as we keep this research moving forward. So on our x-axis, we've got kind of the proportion of match kicks that a player might perform. What percent of the total kicks do they perform? On our y-axis, what percent of injuries do they sustain in terms of the injuries sustained during kicking? So if it was a simple relationship of do more kicks, get more kicking injuries, everyone would lie on that red line. And that's where our fly halves sit, right up the top. They do about half of all of the kicks, they get half of all the injuries. But interestingly, as we start to look at some of the other positions, our scrum half does around a quarter of all the kicks, but only got about 7 or 8% of all of the kicking injuries. And it was our other backs, the back three and the centres, that all lay much more above that line. We don't know why, and that's something we're still trying to work out more. It could be the types of kick they're performing. So scrum halves typically performing these type of box kicks. That's pretty much 80, 90% of their load. Okay, it could be the conditioning they perform. It could be other factors. But clearly there's a discrepancy here in terms of the propensity for injury for different players on the pitch. And this is something we're trying to dig into a bit more to better understand why this might be. And that's, again, another large part of where some of our kicking research is hopefully going in the future. Most importantly, again, then, perhaps just getting back to that focus of trying to make sure we're doing very applied research, a lot of the kicking stuff I've shown you so far has been very lab-based, or kind of with techniques in environments where we've still been attaching things to players, we've still kind of intervened with what they're doing. But we've also been fortunate enough to actually get out on the pitch and do things in real life. And Chris Pocock, who's just in the middle of that slide there, he did his PhD with Jamie North, who's here, and myself at St Mary's, and looked more at the context, taking a more interdisciplinary focus on this. So what were some of the contextual factors that influenced kickers' techniques and performance outcomes as well? And Chris identified that the fatigue, kind of the acute fatigue they were under from a phase of play, and the expectation, the pressure on the kick, were two factors that simply couldn't be ignored. And again, we've had the fortune then with some other applications I've done with John to actually get some of the 20s kickers out on the pitch. This is at half-time in one of the England internationals at Twickenham. So a pretty full crowd, apart from several that are in the bar probably. But we were able to put them in situations where they were experiencing far more pressure than they probably normally would. They had their heart rate monitors on, their heart rates were showing on the big screen. And actually this was then getting them used to performing in those kind of high-pressure environments as a way of hopefully us understanding how their technique held up, and them hopefully learning to cope with that and working with other kind of psychologists and staff within the group to improve that. We've also recently taken it to other sports, particularly to football, which despite all of perhaps the money in football, typically is very underrepresented in terms of some of the science and biomechanics behind its understanding. So John now does quite a lot of work with different Premier League clubs and the FA. And again, we've taken the kit out for various outings to St George's Park or different kind of domes at clubs, and starting to try and understand kicking technique in these applications in free kick takers. How do they get the ball up, over, round, down the wall? How are those best ones able to put that spin on it and ensure a successful outcome? Okay. Final main part of the talk, nice short one, this one. And this is something that, again, a bit of a sidestep from biomechanics. And I got into this as part of a larger kind of Welsh Government project with Liam, where I was going to be initially working on pressure sensors, which is a bit more of a biomechanical application. But this arm of the project took over pretty quickly, and Liam either had the good faith or good humour, I don't know, one of the others, kind of let me loose with this part of the project as well. So this is an area that's built on a lot of Liam's research in understanding heat loss windows essentially. So athletes warm up, they increase the body temperature, their muscle temperature, and a warmer muscle will produce more power. So better performance in our kind of power-based sports. In a lot of elite sports environments, there's these heat loss windows where that heat is then lost. There's cool rooms, there's waiting around, athletes are losing that heat. And there's lots of strategies that have been put in place to try and combat that. So you can see them in the kind of top left, wearing insulated kind of jackets or blankets. More active strategies like Chris Hoy there in the 2012 Olympics with kind of electric heated trousers. And you can see thermal images of those from our lab of what those look like. But they're fairly ineffective. Just little kind of serpentine heaters that don't really get that hot because they can only get as hot as the hottest points, and it's not a very uniform heat. So we were working with Tim Claypole's group in the Welsh Centre of Printing and Coating here in Swansea, and essentially a new kind of technology was developed using printed nanocarbons. So on the screen printers, they were able to produce these kind of heated elements or heatable elements, and then we could assemble them into garment form, wire them up, and actually produce a much larger and more uniform heat across the garment. We've recently started to do some validation of these in the lab, so I'll let you just watch. Hopefully you can see then the kind of heated areas we're seeing in comparison to those typical kind of off-the-shelf wire-based garments, and you can see the heat that's transferred to the athlete's body as well. So on the hamstrings, the glutes, and the quads, and there's also jackets where we can heat biceps, triceps, pecs. And kind of the best proof of this, I guess, came in the fact that last year these garments were taken to the Olympics by British athletes and successful British athletes. So we've still got a hell of a lot to do on this line of work, even though the formal part of the project is wrapping up in terms of the part we've had funded by Welsh Government. But we're now at the point, hopefully, where we've got some really good working garments. Some of the partners in the project are looking to try and commercialise them. We're looking to take kind of them for more of a kind of applications in other sports with the English Institute of Sport, and hopefully lots of ways that this new technology can be applied in the future. So lots to do in each of these three areas still. I've hopefully not just shown that these are kind of dead ends where we're finished. But one other thing that is becoming increasingly important, and again, I've got a few students sort of either recently have worked or are working in this space, is more around the wearable technology side of things. So many sports now are just routinely collecting lots and lots of data with sensors that are based on their athletes, based on their equipment, and we're getting these huge data sets that are potentially meaningful, potentially meaningless, and that's what we're trying to understand. So for Mark's PhD, he spent a lot of time kind of fairly, or in a lot of detail, understanding how much useful information could come out of some of these sensors when they're placed in typical locations where people might put them, the lower back, the upper back, the shin, for example. Okay. And again, this sort of spans back to perhaps what I talked earlier about these methodological considerations, is actually we're trying to take an approach of seeing what value, if any, can come out of these types of signals. Because there's so much information that comes out, but what we want to make sure is we're able to get that insight and turn it into kind of actionable insight for practitioners. And this is where we're hoping to, I guess, go with it, is that we can take these kind of reams and reams of data that they're routinely collected, and we can turn that into some sort of insight that will give coaches and athletes greater medal winning likelihood. But importantly for us, and what we're really trying to do, is make sure it isn't too black box a process. And actually we've got an understanding of the why behind these signals and the information that we're gleaning from them as well. So that's, again, a lot of the work that kind of is going on in a slightly different field to some of these other things I've talked about, but certainly a place where the field's only going to go more and more in the future. A few more people I want to acknowledge, and I've put a few of these faces up at various times in the studies today. These are all the postgrad students and RAs that I've had the pleasure of working with or still working with, who kind of lead a lot of this research that I've talked through today. So it'd be remiss of me not to kind of acknowledge them, given how much they kind of drive and lead all the research that I'm now involved with. They'll also know very well as well that I don't let them get away with doing a presentation without some clear take-home messages. So I need to practice what I preach as well. And I'll go back to where I started in terms of me growing up wanting to play rugby for a living. And I think one of the biggest things that I can only stress is how much of a team effort research is, and how important it is to kind of develop a network, develop good collaborators, and make sure that you've got a team around you who bring different expertise to the table. There's so many ideas and things I've had and wanted to do, and you just don't have the time to do them all. But that's where collaboration comes in and kind of enables these opportunities. And you'll excuse the cheesy animation, but the key thing here is it's an interdisciplinary team. People are bringing different things to the party. Okay, so again, that's something I've definitely benefited a lot from in recent years is, well, unicorns, cowboys and geeks, I guess, if we can describe them, but having a team of people with completely different outlook to me, ultimately. And I still remember my interview when I came to Swansea. I was asked about kind of my approach to multidisciplinary research. And I didn't know whether to kind of challenge it or not, because I don't really want to do multidisciplinary research. I want to work in an interdisciplinary fashion. I'm not going to the nuts and bolts of that, but to me, that's still something that doesn't happen enough. And particularly, again, for students looking at kind of the important differences between those terms, I would really encourage kind of that drive towards working in an interdisciplinary fashion. Really importantly, hopefully, it's all been kind of led by real performance questions in sport. So we're driven by what the coaches need and what they want to know. That's not always very easy to get out of them or to turn them into good research questions, and that's often part of the challenge. But it's such an important thing that all of this research hopefully comes from the real questions that coaches are asking and real things that then they can implement and make a difference out on the pitch with. And finally, I guess hopefully some of the smiling faces through the presentation attest to this, but enjoyment as well. It's a privilege to be doing research with elite athletes. There's enough rubbish we have to do in our academic jobs that isn't enjoyable, but research definitely isn't one of those things. And I think, again, that's something that I always try and keep in mind, is just how privileged we are and how lucky we are to work in some of these situations. When I think back to 18-year-old me who would have wanted to do that and work in these settings. Finally, there's a few people I haven't mentioned. And if you haven't twigged my colour scheme, you might do now, hopefully, in terms of how I've pieced it together. It's also perhaps another cheesy link, because this is probably the people that do link everything I've presented together as well. Firstly, my brother. And I think this picture probably just about sums up our relationship even now, 40 years later. So quite often I'll go kicking and screaming to him, and he'll put his arm around me and help me kind of work out the solution, because he's a biomechanist as well. So we have some really boring Christmas dinners, as Mum and Dad can probably attest to as well. But again, can't thank him enough for kind of the support he's given me throughout my career. On the left of this photo is my in-laws, my wife's parents. Again, since we moved to Swansea, they've been brilliant at supporting us as a family, and I don't think we can thank them enough for the support they've given us. And then on the right, my parents, again, who come today, I can't thank them enough for the support, encouragement, freedom they've given me to do what I want in my career as well. So I wouldn't be standing here and doing the job I'm doing today without their support in many different forms. You can see the girls in there. I think I prefer this photo of them, to be honest. This was about maybe 8 months after we moved to Swansea, and probably just about describes the chaos we kind of moved into as two young kids and suddenly moving west. But again, it's just having that perspective, I think, at the end of the day of what really matters is really important to me. And then finally, Gwen, my wife, who again, I can't thank enough, and she's definitely been the one constant throughout this whole presentation. We met as undergrads on our sports science degree back in 2001. And again, nothing but supportive of everything that I've wanted to do in my career. So I can't kind of thank you enough. And actually, again, I wouldn't be here and wouldn't have done half of these things without your support. That's me. Hopefully, it's given you a bit of an overview. You might have some questions. I'm more than happy to answer, or to go outside and have a drink and answer them out there if you prefer.